Okay, so how do we go about finding a basis for the set S? Right, this is where you take the form of the matrix 2a minus b, b, negative 3b, 0, and you bust out these variables, right? That's the trick. So you try and get them busted out. So when you bust them out, you're going to get 2, 0, 0, 0 times a. And then the b entry is going to be negative 1, 1, negative 3, and 0, right? What this equation really says is that these two individual matrices span S. What's it mean to span the space? It means everything in this space, that would be one of these guys, everything in this space can be reached by a suitable linear combination of those two basis vectors. So these two matrices, therefore, they do span S. In order to be a basis, what else do they have to be? Well, exactly, they have to be linearly independent. Are these two matrices linearly independent? Can you tell just by looking at it? When there's only two of them, when there's only two vectors, it's an easy thing to just look at. Basically, when you have two vectors, the linear independence just comes down to the fact that they are not scalar multiples of each other. You can pretty easily see that, right? I can't multiply the first matrix by a scalar and get the second matrix. Now, if you had three variables to bust out, and you came up with three matrices, then of course you want to be more careful, because it might be that they are LD even though no vector is an obvious multiple of another one. So then you have to go through the more lengthier process of checking for linear independence. But for right here, we can just see it right away. These two matrices are linearly independent. They span the space almost by this very equation. It basically explains that. So they are a basis. Okay, so the basis then, and remember, a basis is a set of vectors. It's always just a list inside of these squiggly braces. It's just a list of those vectors that are spanning that space. Right. Okay. Everybody all right with that much? And so what's the dimension? 2. Okay, the dimension of S is therefore 2. That's always an easy question. Once you have the basis, the dimension is just the number of vectors that are in that basis. Okay. Want to go back to a point Erwin made. Erwin was asking me a question a little bit ago. To show that S is a subspace, instead of checking closure under addition and closure under scalar multiplication, what he was proposing is that we actually do this part. Just go straight into the busting out the variables. And he's absolutely right that we could have done it that way. Because what we could have done is, based on this equation, we could actually have said that S, the subspace we're trying to look at, is actually the span of these two matrices. Right? It's just the span of those two things. And that is pretty clear just from this equation. And one of the things that we learned, right, is that anytime you take a span of a set of vectors, you get a vector space by its very construction, right? This thing is, the definition of this is it is the smallest subspace that contains these vectors that are in this list. So if you reckon, and there's some group works you could go back and practice this with. If you recognize your set as being the span of something, as long as you show me the work that convinces me that, yeah, S is the span of those vectors, then you can say it's a subspace on that basis alone. You don't have to go through these two steps. That's not to say you shouldn't learn how to do this, because I could ask you, is S closed under scalar multiplication? And then you've got to actually do this step, for example. So I want you to be able to do it both ways. You may not always be obvious that S is spanned by something. So if it's not obvious, then you won't be able to do it this way, right? So just something to keep in mind. But that's a very observant point. anytime you recognize your set as being the span of something, it can be justified as a subspace that way. So far so good? Questions? Okay. Let's do another one of the same nature, but that's maybe slightly harder. And I'm reviewing this because we haven't done this since before spring break, and so I feel like maybe it needs a little bit of refreshing. So let's try another example that's basically going to have the same two parts, but it's a little bit trickier. So here it is. This is going to be number 3. So let S be the set of A plus BX plus CX squared plus DX cubed such that A plus C minus 3D is equal to 0. Okay. So very similar problem. We have a set of vectors, and here's what we're going to do in part A. I want to show that S is a subspace of P3 of R. Okay? So P3 of R, remember, that's the set of all the polynomials of degree 3 or less. Right? Now let me tell you what students will often do with this, which is wrong. So don't write this down. Maybe I'll do it in blue, different color here. I just want to show you, be very, very careful, guys, because you get excited about this idea that S is expressible as a span of something. So what I often will see people do is they'll say, oh, okay, so I can just do this. I can just take my polynomial and I can write it as A times 1 plus B times X plus C times X squared plus D times X cubed. In other words, you're busting out the variables, even though they're already busted out, really, right? And so then you're just saying that S is the span of 1x, x squared, and x cubed. Remember, this is not correct. What I'm writing down is not correct. It looks like you've got S as a span of something, which would mean it would be a subspace, and that's the reasoning that people want to use here. But the problem is, well, what's the problem with this? These 4 polynomials are definitely linearly independent, right? If you make a linear combination of these and set them equal to 0, all those scalars will be 0 for sure. They're definitely linearly independent. We haven't incorporated this information at all, right? Nowhere in blue have we talked about this condition right here. So what we've just done right here, what this calculation right here shows, is actually that P3 of R is a vector space, right? P3 of R, the entire P3 of R, this is what a vector in P3 of R looks like, and it's spanned by these 4 things, right? We do know that P3 of R is 4-dimensional. So this is like a basis for P3 of R. But we're not interested in P3 of R in this problem. We're interested in S. S consists not of the entire P3 of R, but only some of the polynomials that are in P3 of R. So we have to be a little more careful and make sure that we are including assumptions like this into the work that we're going to show. So, so be careful. Don't want anybody. Something like this, it seems like a fast answer is too good to be true. And it also will get you very, very little credit at all, because it's hard to give partial credit for something like this, just not really taking advantage of what the assumption is here. So, so let's erase it before anybody gets too comfortable with it. So how should I start this thing off? Yeah, we can try it. We can just go through the 2 steps again: the closure under addition and the closure under scalar multiplication. Okay, so what do you want to have me do to start off closure under addition? Okay, because it's polynomials, I'm going to use a P of x instead of a matrix notation. So P of x would be for polynomials. So let P of x equal A plus Bx plus Cx squared plus Dx cubed. And I need a second polynomial. Let me call it Q of x. And for that one, I need some other letters. Maybe I'll use like a prime plus b prime x plus c prime x squared plus b prime x cubed. Is that all right? Okay, so just, you don't have to use that. You could use like E, F, G, and H if you wanted. Okay, just don't use an x. The x is for the polynomials. But yeah, so something like that. And then b in s, right? Now, because they are in s, I don't want to waste any time. I want to, because the other thing that I will see people do sometimes is they'll say, oh, so I'm just going to add these two together. They get a polynomial and they write element of s right away. But again, they're not using the part in blue here. So we need to use that right away. So I'm going to emphasize that a plus c minus 3d is 0, and a prime plus c prime minus 3d prime is also equal to 0. So we definitely want to write that down. Okay. So we have, we have those assumptions. Okay, now we can add them together. So then, P of x plus Q of x, that's ultimately what we have to do. We have to add these two polynomials together. And we can just do it term by term. So the constant term is going to be a plus a prime. And then the x term is going to be b plus b prime x. And then the x squared term is going to be c plus c prime x squared. And then the x cubed term is d plus d prime times x cubed. So we can do that. And just be careful not to say element of s too fast. I'm going to say it right here, but I'm going to explain it down here. And this is a perfectly good way to do it. But you need to explain why is it an element of s. Well, what's the test to see if it's an element of s? I have to go back to this again. This says my constant coefficient plus my x squared coefficient, whatever it is, minus 3 times my x cubed coefficient, whatever it is, has to be 0. So let me do that. For this polynomial, my constant term is a plus a prime. My x squared term is c plus c prime. And my x cubed term is d plus d prime, so we have a factor of 3 on that. Okay, so this is what we would have. And what do I want this, what do I want to have this equal to?
0.
0. How can I see that it is 0? Say again?
You have to get that form. You have to put, like, manipulate that equation so you can get that a plus
Yeah,
b.
you need to reorganize the terms here, right? You need, there's really 1, 2, 3, 4, 5, 6 terms. You need to group them together so that the terms that don't have the primes are together, and the terms that do have the primes are together. So for example, you have a plus c minus 3d. You want to put that together, right? And then a prime plus c prime minus 3d prime. You want to put that together. So you group these terms in that manner. You group these terms in that manner. And now you have something where we already said that this is 0. And we already said that this is 0. So this is 0 plus 0 is equal to 0. And therefore, P of x plus Q of x is an element of s, which is what we wanted. Yeah, go ahead, Justin.
If we, from the condition we have, could we like solve for a and then plug it into s and then bust it out?
That's the other way to do this. The other way to write this up would be to say, I'm going to just solve, well, you can solve for any of the variables, but yeah, you could solve for a and write a as negative 3c plus 3d, right? You could take that and plug that in for your constant term and then represent your elements of s that way. So instead of having 4 variables flying around, which are a, b, c, and d, you would then only have 3 variables flying around, which would be b, c, and d, right? But then you would have you basically would have built this condition into the form. That's actually also okay. See, the way I did the way I solved it here, I didn't build the condition into how I wrote out P of x and Q of x. I wrote them out kind of just very general. And then I put the requirements later, right? And that's perfectly fine, I like doing it this way, but it's also okay to sort of replace what A equals and what A prime equals into P and Q in the first place, and then just do the addition as before. Okay? Does that answer your question, Justin? Does everybody understand what I'm saying? Okay. So if you prefer to incorporate the condition into the form of P of X or Q of X, you certainly are free to do that. So, okay, so that's closure under addition. Now let's take a look at the, well, the scalar multiplication is going to be a breeze at this point. So we'll do it just real quickly here. Okay, so for closure under scalar multiplication, how am I going to do that one?
Let P of X be as above.
Okay, let P of X be as above. And what else? Exactly, K is an element of the real numbers. Okay, so we'll put that down to set things up. Alright, then we just have to look at K times P of X. And of course, that's just going to be Ka plus KBX plus KCX squared plus KDX cubed. And I would like to show that this is an element of S. Let me just format it the same way that I did the last one. I'm going to go ahead and say that it's an element of S right away, but then I'm going to justify it on the next line. I have to explain why is it an element of S? Well, I have to check this requirement. This is the requirement for being an element of S. So the constant term, which now is Ka, plus the coefficient of x squared, which here is Kc, and then minus 3 times the coefficient of x cubed, which here is Kd, this needs to equal 0. How am I going to show that this is equal to 0? Exactly, I'll pull out the k, that'll leave me with a plus c minus 3d, and this is why I like the saying let P of X be as above, because you get to go back here and say, oh, I already set things up for P of X. I know that a plus c minus 3d is 0. So this is k times 0, which is 0. Okay, so we have a subspace. We have a subspace. Okay. So part B is going to be find a basis and the dimension for this subspace. So, any questions on part A? Okay. Let's try to find a basis and dimension. Okay, so again, guys, when you're finding a basis and the dimension, if you just pull the a, b, c, and d out of this thing and then tell me that the basis is 1x, x squared, and x cubed, that's going to be death, right? You don't want to do that because you're not using the condition when you do that. So you have to be a little bit more careful. So part B, find a basis and the dimension of S. Okay. Let's see if we can figure this thing out. Okay. So any suggestions? So what I've been saying basically is you're not ready to just bust the variables out of here. And that's because, why can I not just bust the variables out of here?
You have the restriction.
I have this part I have to be mindful of, right? So this limits which polynomials are actually in the set. So how do we incorporate it then?
Could you substitute that in there and then bust the variable?
Substitute this into here?
Yeah.
So how would you like me to do that?
So a equals negative c plus 3.
Okay, so we could do that, and then you want to substitute for a over here, right? Okay, perfect. So let's do that. A plus bx plus cx squared plus dx cubed can be written as negative c plus 3d plus bx plus cx squared plus dx cubed. Okay? And now you have the form of all of the polynomials that are in S. So now, as Bastian suggested, you can bust out the variables. But you only have 3 variables, because you got rid of the A. When I bust out the B, I'm going to get B times x. When I bust out the C, I'm going to get -1 plus x squared. And when I bust out the D, I'm going to get 3 plus x cubed. Okay? So you now have a spanning set consisting of these 3 polynomials. So your basis is x, -1 plus x squared, and 3 plus x cubed. Is it clear that this set is linearly independent?
No.
Not as clear as last time, because I have more than 2 vectors. So this is where we've got to be careful, guys. I don't want you to just say, oh, these 2 aren't multiples of each other, and these 2 aren't multiples of each other, and these 2 aren't multiples of each other. You can't use that kind of reasoning, right? But there is, well, of course, we have a way of checking for linear independence. Maybe it's worth reviewing that right now, as long as we're at it. So what I'm going to do over here on this board is I'm going to check the linear independence part. Okay? I'm going to check the linear independence part. If you remember how that works, basically you start off with a linear combination of your vectors, and you assume that it cancels out to 0 to begin with. So if we assume that C1 times x plus C2 times -1 plus x squared plus C3 times 3 plus x cubed, if we assume that that equals 0, then what am I trying to show? That they're linearly independent, but now what am I trying to show in the context of how I started it off?
C1 is C2, C2.
All constants are 0, right? That's what I want to show. Well, if you just kind of multiply this thing out, you have a constant term, which is -C2 plus 3C3. And then the x term is just C1. And the x squared term is C2. And the x cubed term is C3. So there's your equation. You basically have to have, in order for a polynomial to be 0, always 0, the constants that are in those boxes have to all be 0. It's the only way it'll work, right? Well, that actually shows you that C1, C2, and C3 are 0. That make some sense? I mean, you can also view this as like a system of equations. And so you can think of it as, well, that has to be 0, and then C1 has to be 0, and C2 has to be 0, and C3 has to be 0, and then you can put this into a matrix if you want to, right? You can make an augmented matrix out of this thing. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Notice that the columns, so this is maybe what you remember better about how to check linear independence. You're essentially putting your vectors, these are your vectors, you're essentially putting them into the columns of the matrix. It's just that you're not putting the actual polynomial in there, you're just putting the coefficients. So notice your first vector is just x. Well, that's represented in this first column because you have no constant term, one x term, no x squared term, and no x cubed term. The second column is -1 constant term, no x term, one x squared term, and no x cubed term. That's exactly this polynomial. And then the third polynomial is really this one. 3 is the constant term, and 1 is the x cubed term, right? So the vectors have ended up, I should draw these lines here, the vectors have ended up in the columns of a matrix, and now you just have to row reduce it, and you can clearly see that there are no free variables. No free variables means that the solution is just all 0. Did you have a question?
Yeah, could we just do the Dvorsky and take a derivative of that?
Oh, the Wronskian is a, that's a good idea.
That's lost.
Now that we've learned the Wronskian, we didn't know it back in chapter 4, but yeah, you could say, well, I want to check these functions for linear independence, let me put them into the Wronskian matrix and just take that determinant. Some people prefer that. That's totally fine. It only works though if the type of vectors that you're talking about are vectors that you can differentiate. So if I give you a collection of matrices and I say, are these linearly independent? Well, you can't really take the derivative of a matrix. So in that case, you're going to be stuck with this more classical approach, which is, why I wanted to make sure I reviewed it a little bit. Okay. But yeah, so these are, let me give you another reason. Okay, here you go. Here's another reason why I know that these three are linearly independent. Okay, so you have multiple proofs, right? Here's the first proof here. This is the traditional definition. Here's putting the vectors into the columns of a matrix approach. Then we have Brandon's idea about taking a Wronskian of the three polynomials. And there's even a fourth way to think about it, which is that I think everybody here would agree that the first two vectors are definitely not scalar multiples of each other. So if I only had the first two vectors, they would be Li. But then the thing that you're going to notice about the first two vectors is that as you start taking linear combinations of those first two vectors, you're never going to be able to get something that has an x cubed in it, because you're taking a scalar times x and another scalar times -1 plus x squared, which means that this last polynomial is outside of the span of what the first two were able to span. So by throwing this polynomial in there, you're not creating a linear dependency. Remember, linear dependencies are where you can write one of your vectors in terms of the others. We don't want that to happen here. But I'm telling you, this third vector could never be written in terms of the first two because it's got an x cubed in it. So that's kind of just conceptually a way to think about it as well. Okay, so there's several different perspectives on this question, but they're all worth thinking about. Okay, so last but not least, what's the dimension of my space going to be here? 3 polynomials in the set, so it's a 3-dimensional subspace of a 4-dimensional vector space P3 of R. Okay. Excellent, excellent, excellent. So far, so good. Okay. We're making pretty good progress, actually, to tell you the truth here. Let me stick with the linear algebra for another problem or so, and then I'm gonna try and mix it up a little bit, just so we're not getting too heavy on any one thing, but I'm trying to focus on some stuff that I think people would especially need to see. So here is number 4. It says the following. I'm going to define T, and T is going to go from M2 of R to R squared. So this looks like what kind of a, where is this material coming from? Yeah. Linear transformations, right? This is in chapter 5. This was on the second exam also. So define this via, so I have to give you a formula. I'm going to input, say, A, B, C, D, and I have to output a vector in R2. So I'm going to use A minus B minus 3C, comma, 2B plus D. So that is my function, capital T. And I have a 2 or 3 parts to ask you here as well. So the first thing I want to do is I want to practice how do we show that T is a linear transformation. So that's the first question. Show that T is linear. T has to, it's a 2-part process. First part is show that T respects addition. Oh, did it go off?
I know what camera phone.